Welcome back to ECE 442-542. One day or one class period prior to exam number 1, we will, the next time we meet here in this classroom, be having exam number 1. Before you turn in for the, well, maybe I shouldn't say it that way, before midnight tonight, you may not go to bed until 4 or 5 a.m., but before midnight tonight, make sure and submit your homework number 2, which is due today. We will have a review session right after class, well, a few minutes after class if I still have a voice, and that will begin at 7 o'clock in this room. And you should have access to different practice exams on D2L in the module labeled exam number 1 material. And I've also, how many did get an email from me this afternoon? If you've been in your email contact, there's one more chapter that I've uploaded onto the D2L site dealing with Z-transforms. And in that email, I tried to give you the list of topics in that. It may look long. It's maybe 60 pages, but there's a lot of pictures. So there's a lot of figures, a lot of code, and I think you can read it fairly quickly, but that might give you a better feel for some of these topics related to the Z-transform, and we'll be covering those even more in depth by exam number 2 when we start dealing with the inverse Z-transform. In this period for exam 1, we want to be able to go in the forward direction and find the Z-transform. Today in this class period, I want to quickly just tell you what the process is for exam number 1. We will pick up with where we left off last time and try to cover what the frequency response looks like for capital H of little z. What does the frequency response, or how can we find frequency response information given a transfer function? And we'll continue with our review of the continuous time case. We'll finish the derivation of h of z. First, we have to find a difference equation from a differential equation. And then we'll look at the frequency response, which, in fact, now instead of walking up the imaginary axis in the S-plane, now we don't have to walk so far, do we? We just have to walk around a unit circle. We don't have to go an infinite distance to find the frequency response. In the discrete time setting, we actually have a finite distance to walk through or move through in order to find the frequency response. Then if we have time, we'll look at the region of convergence in a little bit more detail. You don't have to know that much about the region of convergence for exam number 1. You will want to probably know for homework 2 something about what happens to the region of convergence for one-sided sequences, where that one-sided sequence is non-negative values of the time index n, or for causal systems, or for n equals 0, n equal 1, on up to positive indices on n. And in those cases, typically the region of convergence is going outside of some circular disk in the z-plane. And we'll talk a little bit more about the region of convergence. The reason we need the region of convergence is so that we can find a unique answer if we start doing the inverse Z-transform. Without that region of convergence, I could give you a couple of different time domain sequences that would have exactly or an equivalent Z-transform expression. But with the Z-transform expression and the region of convergence, that now locks down a unique time domain sequence. That's what I hope to get to, but that won't be on exam number 1. If we get to that, don't fall asleep. but that will be exam number 2 material. Although, granted, we may have a little of that on exam number 1, but I think you know how much of that you will be responsible for exam number 1. The process. Here's what you can bring to the exam. 1 sheet of notes, and that's 8.5 inches by 11 inches, front and back. You can also bring 1 more page that contains a table of z-transforms. I've given you 1 such table in D2L. If you don't like that table, if you're taking another class, if you like another table, you can bring that, but just confine it to 1 more page. Don't bring in another, well, this is what we were given for another class. Condense it down into 1 page. So now you have 2 pages, 8.5 by 11 for your notes, front and back, and an additional sheet of transforms. Is that clear? For a calculator, I don't want you to bring in a big tablet that's essentially these are pretty powerful calculators. That's all you need is a TI-89, a TI Titanium, a TI Inspire, or an HP 51. Up to those. If you have a TI 12, I don't know, what's an earlier version, or if you have a 4-function calculator, that may be sufficient, but you might want some trigonometry on your calculator, some trig operations or functions. That might be helpful, something to write with, pencil or pen. And I would suggest, even if you have a pen, don't spend time erasing. Just cross it out. If you need more paper, I will try to have some blank paper. You raise your hand and I'll give you a blank piece of paper that you can continue your writing. Who knows, maybe after you get halfway through your second solution, you realize your first one was correct. Then you can say, here, go ahead and look at what I scratched out. And then you don't have to erase and rewrite. What's not allowed, you won't have a computer, you won't have your cell phone, you won't have textbooks, and you don't have class notes. That's the process for exam number 1. Now let's get into the material. Question? Question was, can I leave my answer in equation form? Maybe, but there might be times where you actually want to have a numerical value. I don't know what the exam looks like. I wish I did. It's not yet written, so I can't tell you for sure, but I would say to be on the safe side, bring a calculator. And don't necessarily leave it in some form. Yes?
And you write the exams?
Pardon?
You write the exam?
Do I write the exam? I attempt to write an exam, yes. Good luck, with that. But you can see the style of the exams that I've written in the past. I may be running out of ideas, but there are several exams to look at for practice. And that gives you maybe a feel for the style of an exam that you can expect on Wednesday. We have a way of relating the S-plane and the Z-plane through this relationship. Z, which is a complex number, is equal to e to the st. T is the sample period, and s is a complex number. S is the complex frequency in the Laplace domain, or associated with continuous time systems. Z is the complex frequency variable for discrete time systems. If we found h of j omega, which for stable transfer functions, that's how we find the frequency response of a continuous time system. We simply walk up the imaginary axis. We evaluate h of j omega for different frequencies omega. We're living on this highlighted vertical axis. That gives us h of j omega, and that's how you sketch a Bode plot. H of j omega in general will be a complex number. You can find its magnitude, take 20 log of that, and that's your magnitude plot for your Bode plot. You can look at the phase of that complex number at each frequency, and that's your phase plot for your Bode plot. I did get a question on the quiz, do we need to be able to sketch a Bode plot? I would like to say yes if you're an ECE student. You should be able to, but you probably won't have to on exam number 1. Okay? Good thing I'm not left-handed. Those of you listening at home are wondering what's going on, but I felt left out already. I mean, we've got the Super Bowl last night, we got the Olympics starting. I had to leave my equipment over in ECE so I could run back and get it before class started, just so I don't get left out, so I don't feel like I'm being left out of all this activity, physical exercise that's going on around the globe. Anyway, we're back to frequency response. If we use this relationship, z is equal to e to the st, we evaluate h of s when s is equal to j omega. If we use that same relationship in h of z, we now replace s in e to the st with j omega, and we can actually combine omega with our sample period, capital T, and now just call that a theta. And that's now some amount of radians per sample. If you look at e to the j theta, that's a complex number, but from Euler, that now could be thought of in rectangular form. That's cosine of theta plus j sine of theta. That's e to the j theta. But what is cosine theta plus j sine theta? Magnitude. It's the real part squared plus the imaginary part squared. We have cosine squared plus sine squared. 1. E to the j theta puts us on this arc that's a distance 1 from the origin in the z-plane. That's where we will find our frequency response information for the z-domain, is by walking around this arc that's 1 away from the origin in the z-plane. Give me a frequency, omega. I can multiply it by our sample period t and give us a theta, and that will be some radian measure on that arc. I can now find how the poles and the zeros of my transfer function h contribute at that point in the z-plane, and that will give me how the magnitude and phase adjusts for my frequency response information. This should all be review, and if it's not, it will be by the time we finish today. If I give you a transfer function, a stable transfer function, capital H of S, and I excite that system with a cosine or a sine of a frequency omega 1, that's the little v sub I of t, now I'm shaking that system at a frequency of omega 1. If it's stable, all the natural dynamics will eventually die out, and what am I left with? I'm left with something shaking at that same frequency, omega 1. It's just going to be a modified amplitude, and it will be modified by how that system's magnitude is created at that particular frequency, omega 1. So I'm finding the magnitude of h of j omega 1, and that now is how my amplitude of the input gets adjusted at that particular frequency. It will also be shifted in time by the angle of that transfer function. And again, capital H of j omega is just a complex number. And you can find its magnitude and phase. That's the magnitude here in red, and that's the angle in red. And you can simply plug those in to adjust your original input to a sinusoidal steady state output. That's what the SS means. That's the sinusoidal steady state, which means the transients have all dissipated, and we're now left with an output signal that's oscillating at exactly the same frequency that we were shaking the system at, which is omega sub 1. It's just had a change in amplitude and an offset from the input. Cosine wave in this sense, in this example. For a generic example, here I have a transfer function h of s. This isn't looking good. I'm already starting to lose my voice, and I have another how many minutes? Anyway, we'll see how it goes. We now have 3 poles and a 0 for capital H of s. Each of those poles and 0, each of those singularities contribute some to the magnitude response and some to the angle or phase response of that system H. And if your system is written in pole 0 form, it will have a 0 factor, it will have pole factors, and it will have some gain constant that I'm just representing as an alpha. But if you had sketched this pole 0 diagram accurately in the horizontal and vertical direct dimensions, you could pull out your dividers. Everyone knows what dividers are, right? You've taken your drafting class. Now it's all computer drafting. Well, we used to have these dividers that were dangerous. If your instructor was mad at you, they have needles on the end, and they sometimes got thrown around the room. That was back before everything was maybe as well protective of the student. But you now have dividers that you can measure distance. You could use an old-fashioned ruler and measure those distances from the pole to j omega 1. Or you could compute, if you had a calculator, you could compute that hypotenuse numerically. That's all we're calculating, is that hypotenuse for these different values. And if we had a calculator with the trig operations, we could do the inverse tangent and find these 3 pole angles and the 0 angles from that diagram. This information for h of j omega 1 now can be separated and simply use the length information or the distances to find the magnitude of h at that frequency, and the angle is just the angles of the numerator minus all the angles of the denominator. The denominators are downstairs, so you subtract those angles. The numerator angles are upstairs. Yes? Where does alpha come from? Alpha comes from the whatever it started out being. For example, you might have had 6s plus 4 over s plus 1, s plus 2. I'm getting very creative. S plus 3. 1, 2, 3, 4. That 6 is the gain that comes out after you've essentially normalized all of these coefficients on s to 1. That's the alpha. In this case, alpha would be 6, and that's in pole 0 form. And that obviously then impacts your magnitude at a given frequency. If somebody changes the frequency of oscillation, you simply do this process, except now you change where you're evaluating at. Maybe it's now at that location, which is 2/3 of the original omega. But you now draw these lines and angles to that yellow highlighted point, and that's now your oscillating frequency that you're exciting the system with, omega sub 2. And you can see then that as you go from DC, where is DC on this pole zero diagram? DC is right here. You go from zero frequency all the way up to infinity, and that now gives you your frequency response. The discrete time case is very similar. We should, by Wednesday, know how to find a transfer function for a discrete time system, either from its difference equation, from its state space, from its block diagram. You should be able to find a transfer function. If somebody then excites it with an input, you can then, because you know that you can now form products in the frequency domain, you can now find the z transform of the output, v sub 0 of z, by just that product of h of z with v sub I of z. If, in fact, you have a stable transfer function, and what's a stable transfer function in discrete time correspond to? So the poles are strictly inside the unit circle, aren't they? They can't be on the unit circle, because then I could find a bounded input that would cause the output to go unbounded. We want bounded input, bounded output stability. That means all of the poles of h of z have to live strictly inside the unit circle. And if that's the case, and we excite this system with a sinusoidal input, a cosine or a sine, at a given frequency, here I'm going ahead and calling that frequency in terms of theta 1. Theta 1 has units of radians per sample. Buried in there, if this came from a sampled continuous time, theta 1 would be omega times the sample period, capital T. But I could have a generic discrete time system where it's not coming from a sampled continuous time system, it's just a discrete time system, and I'm just given theta sub 1. The structure is identical to what we had for the continuous time case. We simply evaluate h, and where do we evaluate h for a frequency response? H of z. Don't make me pull out my dividers. I need to bring a pair of dividers. That'll strike some fear in you. If you weren't nervous on Wednesday, you will be. So now you're looking at the unit circle, aren't you? You want to now be evaluating h of e to the j theta 1, where theta 1 is corresponding to the frequency that you're exciting your system at with this cosine waveform. And there is just a reminder why we're on the unit circle. Because of Euler. If we are now looking at this complex exponential e to the j theta, that now has a magnitude of 1. Simply because the cosine squared of theta plus sine squared of theta is 1. And now we can draw our diagram in the z-plane, consistent with how we set it up in the s-plane, except now we're focused on the unit circle. Now we want to evaluate this at a distance 1 away from the origin. And in this case, what's the order of that system that I'm generically illustrating in this plot? What's the order of that h of z? How many think it's first order, second order, third order, fourth order, fifth order? I had more threes, third order. Why is it third order? I see 4 points up here. I see 3 X's and an O. Why did you vote for 3? It only depends on the poles, doesn't it, the system order. So it's third order based on the 3 X's. If I ask you that question on the exam, that would be a gift. If I give you a pole 0 pattern and I say, what's the order of the transfer function associated with this pole 0 pattern? 1, 2. You don't need your calculator for this. You can actually count up the number of X's, and that will give you the order. This one's third order, so now we have 3 angles due to the poles. We have 3 lengths from each of these X's to the point in question, and that point is determined by the angle theta 1 that point makes with the horizontal real axis. Theta 1 is going to be some amount of radians. You simply measure that, or you convert it into degrees and pull out your protractor and measure that angle. And now you have all of these angles are relative to this horizontal line going to the right from each of the poles and zeros. That's how you measure your angles for each of those singularities. The distances, again, are determined by this right triangle's hypotenuse. Yes?
For the number of poles in this loop, is it only the finite ones, or is it like all of them?
So now the question was, the poles that I'm referring to on the system order, does that only involve the finite poles, or does that include the poles at infinity? It's only the finite poles. So it's only the poles that are visible on the finite plane in Z. And we probably won't have infinite poles, because that would mean that our numerator polynomial was of higher order than our denominator polynomial. We'll stay away from that. But this is now, and the beta comes just like we had the alpha before. This beta is just this gain that comes out after we factored out the coefficients associated with each of the z's in our zero and pole factors of h of z. We then can identify the magnitude characteristic of our h of e to the j theta 1 at that frequency by simply using the different lengths from the zeros and the poles, and the angle is just the difference between the zeros phase summed up minus the pole angles summed up. Again, numerator angles minus denominator angles. That's how we will use it. Now let's see if we can actually work through how we find an h, capital H of z. Let's pick up where we left off last time. So this is sort of an advance of where we want to go, how do you use this capital H of Z, we can use it actually to figure out how our discrete time system will move in response to sinusoidal inputs. And this is how we could compute it, either graphically or analytically. Each of these lengths could be computed numerically, and the angles could also be computed with your calculator. Here's where we have been from last time. We started with something that I hoped you felt comfortable with, which is an RC circuit, first order, and that we can use to create a low-pass filter. And you should be comfortable finding the differential equation of an electric circuit. For the exam, yes, you better be able to find the dynamics, the equations of motion, how this electric circuit is described in either the S domain or in probably the S domain. I'll probably have you finding something in the S domain, and probably more than a first order circuit. Probably not a 10th order, but somewhere in between. You've already done a 4th order, haven't you, on a homework? 2 inductors and 2 capacitors. All right, here was a first order. We ended up with a first order differential equation relating the output voltage, the voltage across the capacitor, how that's related to the input voltage applied across the series combination of the resistor and capacitor. And I think last time we excited it at 500 radians per second in the continuous time setting, and we figured out that for a filter that had a bandwidth of about 100 hertz, we would be a little bit down from 2 at 500, because where is our break frequency? At 100 hertz. In the Bode plot, where is our kink in our magnitude? Or where does it start in the straight line approximation? Where does it start sloping? 600 was our approximation, wasn't it? We didn't worry about 628, but that's a straight line approximation. The actual curve is rolling off between those straight line asymptotes that we've sketched, and that's why, even though we're not yet to 600, we have seen some attenuation in the amplitude from 2. We've collapsed. At 600, what would we be down? We would be down at 0.707, or we would be at 1.414. We would be 3 dB down at the break frequency. And we're not quite to 600 when we excited at 500. And we had a little bit of a phase shift, a delay between the input and the output of about 40 degrees. And you know that if you start computing 500T minus 40 degrees, there's inconsistency in those units. That's just the convention. So you would have to make sure that you converted either radians to degrees or the degrees to radians before you combine those two quantities. 500T can't be directly combined with 40 degrees. 500 is in radians per second, so omega T will give you radians. And you know how many radians are in 360 degrees. 2 pi. And that's how you would convert between those. What we want to do now is find the discrete time approximation to that first order differential equation. We want to find a difference equation that will approximate a first order low pass filter with a cutoff frequency of about 100 hertz. That's what we want to achieve. So we want to now find a way of getting from this differential equation to a difference equation. And I think last time this is sort of where we finished. We said we are going to do a crude discrete equivalent. So it's not really an equivalent, it's an approximation. And the approximation that we are using is going to be approximating this derivative with a forward difference. That means we're going forward in time to create this difference, this delta in our output over our delta in the denominator. So we have delta V naught over dt. We can find a small variation in V naught by comparing V naught at time n plus 1 with V naught at time n, where typically I don't even worry about capital T. I just say n minus 1 minus V naught of n. And that will then be divided by the difference between n plus 1 times t minus n times t. If you distribute that n plus, or the t in through the n plus 1, you can see that our denominator ends up being simply equal to our sample period, capital T. So that's what we're going to do. We now have V naught of t, V naught prime of t being approximated by V sub 0 of n plus 1 t, V naught of nt all over t. How do we find capital T? We need that to keep going. How far apart in time are we sampling each point? Do we know anything about this system? We're approximating a low-pass filter with a difference equation. What do we know about the low-pass filter? We know the time constant of that low-pass filter. We know its bandwidth. We could use either of those to try to figure out what capital T is. I'm going to use the cutoff frequency, or the bandwidth, in radians per second. We know, or we allowed, omega sub c to be 600. And that, we're not going to speed up the system. We're not going to make the bandwidth wider. We wanted 100 hertz, or approximately that. So we said we'll be happy with a bandwidth of 600 radians per second. We're not going to make it 1,000 or 1,200. If this is now our sort of fastest frequency that we're interested in, how do we relate that to our sampling frequency, omega sub s? What's our rule of thumb? 30 times that. And that's a rule of thumb. That's not a exact expression or quantity. It's just something to get us an answer. So we're looking at sampling at 30 times 600, or 18,000 radians per second. We could relate that to the sampling frequency in hertz or cycles per second, or we could use that value for omega sub s to solve for that capital T, the sample period. If we solve this for capital T, there is now our capital T. Or T is approximately, what, omega sub s was 18 times 1,000. So there's a 3 downstairs. You know what I want to do with pi, don't you? Don't get me hungry. We want to round pi from 3.14, and we can go down. That's the best way to approximate or create a capital T, is to shrink it instead of making it bigger. So we're going from 2 pi, 2 times 3.14, to 2 times 3. Or now this becomes 1/3 times 10 to the minus 3. So we're now sampling at 0.333 times 10 to the minus 3 seconds per sample. That's how fine we're resolving the time axis. Now we can convert our differential equation into a difference equation. That was our time domain differential equation. We're approximating this derivative with the forward difference. Which means that all of the current instances of time, we're using t equaling little n capital T. And that derivative, we're using the forward difference, which now says, oh, go forward in time to make that delta V naught in the numerator of that derivative approximation. And we usually want to solve this for the highest index of V naught. So we can now clean this up by multiplying by capital T divided by tau, everything in that expression, and that will give us a coefficient of 1 in front of V naught of n plus 1 t, so that now we have V naught of n plus 1 t minus V naught of nt plus t over tau V naught of nt equaling t over tau V sub I of nt. Tau, if we remember what that was based on the bandwidth of our low-pass filter. That was 0.00167, or 1.67 times 10 to the minus 3. And capital T was 0.333 times 10 to the minus 3. So if you look at capital T over tau, if you do the 10 to the minus 3's cancel, and we have 1.67 divided by, or that's 5/3 divided by 1/3. Is that right? I'm sorry. 1/3 divided by 5/3. We had the tau, which is 5/3 downstairs. T, capital T, is 1/3, so that we now have 1/5, or 0.2, for that ratio of capital T to tau. And 1 minus 0.2 is 0.8. And now we have a fairly clean difference equation. Everybody knows that's a first order difference equation. We have just one time shift between the dependent variable V naught. So this is a first order difference equation that produces a low-pass filter with a bandwidth of approximately 100 hertz. Everyone comfortable with that difference equation? this you could now use in a computer program if you wanted to. If you needed to filter data, noisy data that you wanted to low-pass filter that had been sampled, how fast? Well, it would have to be sampled at 0.333 times 10 to the minus 3 seconds per sample. But if you now have data coming in, a sequence of numbers that had been sampled that way, you could put it through this difference equation, and out V naught would be a filtered version of that. V sub I would be the input sequence of numbers. What if we actually excited this system, this low-pass filter, with a sinusoid? And to be consistent, let's excite it with what we excited the continuous time filter with, or an equivalent signal. What if V sub I of nt is 2 times the cosine of 500, and now instead of t, little t, it's the sampled version of that. That's little n, capital T, where capital T is 0.333 times 10 to the minus 3. Or V sub I of nt is, now we can multiply 500 times 1/3 times 10 to the minus 3, and we end up with 2 times cosine of 0.1667 n. Where this guy, this theta, let's say theta sub 1, that's where that came from. We want to know how this system, how this low-pass filter is going to change or respond to being shaken by this sequence of numbers that will be a cosine of amplitude 2, and we know how that is shaking with time. We have its radian per sample angle, or its frequency. What do we need, or what's one way that we could simply simulate this? You could produce this sequence of numbers, V sub I of n, for n equal to 0, 1, 2, 3, just by evaluating this in a spreadsheet, in a computer program, by hand. You could generate different values of that cosine. But how else do we know how to find it? In addition to numerically. What did we talk about at the beginning of today's lecture? How do we know V sub 0 steady state differs from V sub I of nt? By the transfer function. If we had the transfer function, we could evaluate that transfer function somewhere and use that information to relate V sub 0 of steady state to V sub I. So we need the transfer function. we have the difference equation. Is it okay that I've dropped the capital T in my argument? We have that on the side. You're all familiar with, at a restaurant, you say, can I have that on the side? Well, you just take that T and put it on the side. You have it on the side of your paper, right? It's 1/3 times 10 to the minus 3. If somebody needs that actual time, you can tell them what's little n? It's 10. Oh, I now know what the absolute time is. It's 10 times 1/3 times 10 to the minus 3. We want the transfer function. We can find it from this difference equation by z transforming. What do we need to do about the initial conditions? If we're interested in the transfer function, what do we need to do with the initial conditions? Do we need to do anything with the initial conditions? No, we want to know what's happening in the sinusoidal steady state. All the transients have disappeared. We don't care about what the initial conditions are, so let's go ahead and neglect the initial conditions when we take this difference equation into the frequency domain. And now, how does little v sub 0 of n plus 1 of capital T move into the frequency domain? So if I now z transform v sub 0 of n plus 1 versus the z transform of v sub 0 of n minus 1, how do those relate? Carefully. And what's the z transform? If you're looking for extra credit, you'd probably write that down on your paper, wouldn't you? And say that. You would say, let the z transform of little v sub 0 of n equal capital V sub 0 of z. If that's the case, how are these top two expressions evaluated when we neglect the initial conditions? What's a delay operator in the frequency domain? That's the z to the minus 1. But what do we actually have? We have an advance of 1. The delay is z to the minus 1, and advance is z. Are we now on the same page? Now we know how to put little v naught of n plus 1 into the frequency domain. We say that that's z, v sub 0 of z, equaling 0.8. And we just said, well, that's just capital V sub 0 of z. What do we do with little v sub I of n when we z transform it? Just capitalize it. We hit the shift key. We now have v sub I of z. Oh, I didn't ask for help. I guess it thought I needed it as much as I was trying to hit the screen. Hopefully we'll be okay. But now I can combine this. I now have z minus 0.8 capital V naught of z is equal to 0.2 V sub I of z, or my transfer function that I was after there's my transfer function of a discrete time low pass filter with a bandwidth of 100 hertz when we're sampling at 1/3 times 10 to the minus 3. So that now we can think of our question in terms of this block diagram. We have an input hitting or exciting a transfer function and producing an output. Graphically, what do we have? What's the pole zero diagram of this low pass filter? Do we have any open circles? Any finite zeros? No. Do we have any finite poles? We have one at 0.8. Our pole zero diagram is that simple. You can draw a better circle, but that's now a quarter of the unit circle. What do we want? We're now exciting our system with this input, this cosine, and we want to know what's V naught of S. Do you know where on the unit circle we might be interested in evaluating this pole zero diagram? We're walking along this unit circle. Where do we stop in order to find the length and the angle relative to that pole? Is it anywhere on this screen right now that could help us figure out where we need to be? What is this? Theta 1. What are the units on that theta 1? Radians per sample. When we hit it with sample, we're going to have a radian. We now need to convert that 0.1667 radians if we wanted to think in terms of degrees times 180 divided by pi, roughly 60. So we're now looking at going along that unit circle until we reach a point that we're at 10 degrees relative to the origin. I might exaggerate that, but now we have this point right there. This is our angle, theta 1. This is e to the j, theta 1. Where theta 1 is approximately 10 degrees, 9.55. We could get out our ruler and measure from here to there if we wanted to. Or you could do it analytically. You could find that e to the j theta 1 in rectangular coordinates using Euler. You know, cosine of 10 degrees will give you the real part. Sine of 10 degrees will give you the vertical part. Now you have the rectangular coordinates of that point on the unit circle. You know where the pole is. That's at point 8. What's the expression, or what's the structure of our sinusoidal? Are we going to reach a sinusoidal steady state for this filter? How do we answer that question? Will we end up being in a sinusoidal steady state, or will we go unbounded? How do we determine that? We want to know where are the poles relative to the unit circle. Are our poles inside the unit circle? For this low-pass filter, yes. We had one pole and it's at 0.8. So it's stable. We will reach a sinusoidal steady state movement. And what's going to be the structure? We started with an amplitude of 2. How does that 2 get changed? It gets changed by how the low-pass filter shakes at an angle of 10 degrees. So we're now looking at the magnitude of h at e to the j theta 1. Cosine, what frequency is it shaking at? If we're shaking a system at 3 radians per second, is it going to end up shaking at 27? No. If it's a linear system, it'll start shaking at 3. This one's going to shake at exactly the same frequency that we were exciting it at, and that was determined by theta sub 1. So the cosine is going to be 0.1667 n. It may be a little bit delayed or adjusted in time relative to the input. And what's the phase change? That's the angle of our transfer function, low-pass filter, evaluated at that same frequency on the unit circle, determined by theta sub 1, e to the j theta sub 1. And if you wanted to find that, then numerically you could say, well, I'm going to let z equal e to the j theta 1, which is e to the j 0.1667, or that's now 1 at an angle of 0.1667 radians. Or if you wanted it in rectangular form, it would be cosine of that plus j sine of that. Our numerator didn't depend on z. It was just 0.2. Here's where our z was. Now we pull out Euler, and we have cosine and we just have to remember how to perform complex algebra. We have a complex number in the denominator, which if we evaluated this, again, that's cosine of 10 degrees. That's going to be what? Pretty close to 1. It's 0.9861. Sine of 10 degrees is pretty close to 10 degrees, or if we use radian, it's pretty close to the 0.166 that we had. It's 0.1659. Remember the approximation, sine theta is approximately theta when theta is small. So if you didn't have your calculator, you could just say, well, I'm going to approximate this and let sine of theta be 0.166. And you would be pretty close. And then we subtract 0.8 from the 0.986, and we end up with 0.2 over 0.18614 plus j 0.1659. To divide, it's easier to do it in polar form, the denominator, or we could multiply top and bottom by the conjugate of what's in the denominator to clear out that complex number. Here I went ahead and converted it to polar form. Now we know how our amplitude has changed. It's reduced by 80%, and our phase shift in degrees is now 41 degrees. Or for the discrete time sinusoidal steady state, we now have 2 times 0.8 cosine 0.1667 n minus 41.710. And if you were looking at this z-plane plot from before, we've actually found what this point is right here in our earlier analysis. This was 0.9861 plus j 0.1659. Where this distance was our L sub p, and this angle is theta sub p. Where L sub p is now this 0.9861 minus 0.8. That's the change in the x direction, or horizontal. And the vertical direction is 0.61 or 0.1659 to give us an L sub p of 0.2493. And the theta sub p we have a vertical change of 0.1659 and our horizontal change is the difference between that 0.98 and the 0.8. Question? That's how you could start checking your work, is going back and sketching this and saying, does this really make sense with what I just calculated? You could perform this analysis somewhat graphically in your z-plane and say, oh yes, this starts to make sense. I can actually see what L sub p is and how that influenced my magnitude response. And you could compare this discrete time answer. This is now 1.6. That before this time shift, wasn't it about 40 degrees in the continuous time setting? And what was the amplitude? 1.5 something? So we're doing about the same with this discrete time low pass filter in a difference equation as we found in the continuous time setting. We didn't get into region of convergence. We'll save that until after the exam. Good luck on the exam, and I'll see you either in a few minutes or on Wednesday.